So there's 125. That is my one and only critical point. I need for that critical point, and this is A prime of x, label things correctly, I need for that critical point to be a, all the way back up here, maximum. What dimensions will maximize the total area of the pen? So when I plug, let's go back here to the derivative function, there's A prime. When I plug 100 in, I have 100 minus 400 over 5. That's 100 minus 80. That is a positive value. When I plug 150 in, that's 100 minus 600 over 5. That is a negative value. I do indeed, according to the first derivative test, have a maximum when x equals 125. Now the question asked what dimensions. It didn't say what x value. It said what dimensions. I have to find a corresponding y value. But that's pretty easy to do because I found a relationship between x and y. So I can come back down here, and when x is 125, y is 100 minus 2/5 of 125. 5 goes into 125 5 times. That's 100 minus 2 times 5, or 100 minus 10, that's 90. When they ask me in words, I answer in words. The dimensions. That will maximize area are, what units are we in? Are we in feet? 500 feet of fencing. So those dimensions are 125 feet by 90 feet. And there's your first optimization word problem, your first max-min word problem. So let's work this example. A sheet of cardboard 3 foot by 4 foot. I'm going to start drawing a picture as we go here. A sheet of cardboard 3 foot by 4 foot will be made into a box by cutting equal-sized squares from each corner. Equal-sized squares from each corner. And folding up the 4 edges. So I'll just, here, that's actually going to be cut out. And we would fold along there and along here, and I think you can begin to see how we would wind up with a box with 4 sides. What will be the dimensions of the box with largest volume? And I'm looking at length times width times height. That's going to be a rectangular solid. So that's all I have. That's all I know. I have a rectangle. We're cutting equal-sized squares from each corner and folding up the 4 edges, and then we want to maximize that volume. So I'm going to call that cut that's coming out of there, I'm going to call it X. I like X. X makes me comfortable. I notice that once this fold has been made, the height is actually going to be X. So that's helpful. Let's see if we can come up with length and width, I know that the whole thing has a length of 4, but this has been cut out and that has been cut out. So the actual box just has this length. How could I write that in terms of x? Well, the whole thing is 4, and I've cut one x out and a second x out. So this distance is actually 4 taking 2 x's out. That's how I could write the length in terms of x. And you'll see that may look new to you, but you'll see situations over and over and over and over again where that technique's going to work for you. So maybe you never intuitively would have thought about doing that. Don't worry about it. It'll become much more natural the longer and longer and longer you do it. So the same thing here for width. If that whole thing is 3 and I'm cutting an x out here and an x out here, then this distance is 3 taking 2 x's out of it. That's how I'm going to write the width. Now I want you to notice something. There's a term already in terms of x. There's a term already in terms of x. I guess I should say a factor. I don't have to use the step in the process that requires a relationship function. This particular problem does not require a relationship equation. The only thing I use the relationship equation for is to put the optimization equation in terms of one variable. I'm already there. My optimization, what they're asking me to maximize or minimize is volume of this box. And they want the maximum, that's what largest means, they want the maximum volume. So the rest of the process is find V prime. Now I'm differentiating, and we normally don't write it, but I will here just so you stay with me. We're differentiating with respect to the variable that V is written in. Let's clean V up a little bit. I'm going to FOIL out those first 2 factors. I'm going to get a 12, that's first. Outside is minus 8x. Inside is minus 6x. And last is plus 4x squared. And then I would multiply all that by x. So, give myself a little more room here. V of x is going to look like 12x. I'm distributing that x, plus I'm going to combine like terms, minus 14x squared. Negative 8x minus 6x is negative 14x's, times x is minus 14x squared, plus 4x cubed. There is my optimization equation. Now, we're taking time while we're learning it to label. So when you look back in your notes, you'll have everything labeled correctly. But when we actually do these problems, we're not going to worry about labeling relationship or optimization. I'm just doing it for teaching purposes. Now I'm going to differentiate with respect to x. I have 12 minus 28x plus 12x squared. I want to know where that equals 0 or where that does not exist. This is a polynomial function. Luckily for us, lots and lots and lots and lots of these problems, our optimization equations are polynomials. So that makes it much easier. I could definitely factor out a 4. I don't know if that'll help me. Plus, I'm going to write things in an order that I like better. I'm going to put that term first. Let's see, 4 will go into 28 7 times, and then plus 3. This is a quadratic equation. I need to factor. I'm going to divide both sides by 4. 0 divided by 4 on the right side of the equal sign is still 0. So let's see if we can factor this thing. Now, I need a minus 7 and a plus 3. So I'm going to have a 3 and a 3. How am I going to get a minus 7 and a plus 3? I don't believe that, frankly, is going to factor very nicely for me. So I do always have the option of using the quadratic formula. Here's A, here's B, here's C. So it's negative B plus or minus the square root of B squared minus 4 times A times C all over 2A. So x is 7 plus or minus 49, 12, 36. There's why it doesn't factor very pretty. There are the values. So x is either 7 plus root 13 over 6 or 7 minus root 13 over 6. Our values don't have to be beautiful integers or beautiful fractions. They can be anything. These are my critical points. I need to test on either side. Here's test points. Here's v prime of x. Now 7 minus root 13 over 6 is going to be smaller than 7 plus root 13 over 6. Let's see here. Root 13 would be between root 9. Here's how I have to do it when I don't have. That would be between root 9 and root 16. So we are between 3 and 4. So 7, we'll call it something, probably it's closer to that. So something a little bit smaller than 4, so 3-ish. So this is roughly 7 minus 4 is 3. 3 over 6 is 1/2. I'm pretty good at calling that 0, I believe. And if I was to add 4 to 7, that would be 11. And 11 divided by 6 is not quite 2. So I'm okay putting 2 there. And going to be okay putting 1 there. 3x squared minus 7x plus 3. When I plug a 0 in that, I get a positive value. When I plug a 1 in that, I get a negative value. 3 plus 3 is 6, minus 7 is negative 1. When I plug a 2 in there, I'm definitely going to get a positive value. My max happens at this value of x. There is the dimension for x. That's what I've got to cut out of that corner in order to have the maximum volume. Then I have to find my other dimensions. What will be the dimensions of the box with the largest volume? I have 7 minus root 13 over 6. There's one dimension. 3 minus 2 of those is another dimension. And 4 minus 2 of those is the third dimension.